Picture this, a vast cosmic tapestry woven from billions of galaxies, stretching across more than 110 million light-years of space. A structure so immense it makes our own Milky Way seem like a single grain of sand on an endless beach. This is the Virgo Supercluster, our local neighborhood in the grand architecture of the universe, and hidden within its sprawling expanse are mysteries that defy everything we think we know about reality. Have you ever gazed up at the night sky and wondered just how much remains unexplained, even in our own cosmic backyard? Today, we're setting out on a journey to explore 25 of the most baffling, awe-inspiring phenomena tucked within this colossal structure, enigmas that challenge not only our understanding of physics and astronomy, but the very limits of human curiosity itself. From galaxies that spin in ways they shouldn't, to strange gravitational anomalies that hint at invisible forces at work, each of these mysteries invites us to question, to imagine, and to marvel at how much is still waiting to be discovered. Think about it, we're living in an age where technology allows us to peer deeper into space than ever before, yet with every answer we uncover, new questions emerge, pulling us further into the unknown. The Virgo Supercluster isn't just a static collection of stars and planets, it's a dynamic, evolving puzzle, and each unexplained phenomenon we'll explore represents a piece of that puzzle, one that could reshape our understanding of the universe. What if I told you that some of these mysteries might hold clues to the nature of dark matter, the fate of galaxies, or even the possibility of realms beyond our current comprehension? This video is your invitation to join that exploration, to step into the role of cosmic detective and uncover secrets that have puzzled scientists for decades. Together, we'll venture through eerie voids where galaxies seem to vanish, examine celestial objects that behave in ways physics can't yet explain, and ponder questions that stir both wonder and humility. So settle in, open your mind, and get ready to journey through one of the universe's most magnificent and mysterious structures, because what we're about to uncover might just change how you see the cosmos forever. We begin our journey with the most foundational and perhaps most profound mystery in all of modern cosmology, one that literally holds the Virgo Supercluster together yet remains completely invisible to us. Astronomers have known for decades that something is very wrong with the math of our universe. When they calculate the immense gravitational pull needed to keep galaxies from flying apart and to bind entire clusters of galaxies together, the numbers simply don't add up. The sheer amount of visible matter, all the stars, nebulae, and planets we can see, accounts for only a tiny fraction of the gravity that's actually at work. It's like watching a marionette show where the puppets are dancing with incredible energy and precision. But when you look up, you see there are almost no strings attached. The motions of galaxies within our supercluster, particularly their orbital speeds and how they interact with one another, behave as if they are embedded in a colossal, unseen halo of something. This gravitational phantom, which we call dark matter, is estimated to make up a staggering 85% of all the matter in the universe. But what could it possibly be? The leading theory points to a class of hypothetical particles known as WIMP, or weakly interacting massive particles. These exotic particles would barely interact with normal matter or light, which is why they've evaded direct detection for so long. They simply pass through our telescopes, our planets, and even our bodies without a trace. Yet their collective gravitational influence is the dominant force sculpting the large-scale structure of the universe. However, after decades of sophisticated experiments built deep underground to shield from cosmic interference, not a single definitive WIMP has been caught. This continued failure has led some brilliant minds to propose a radically different solution. What if we've been looking for phantom matter when the answer lies in phantom physics? Theorists like Mordechai Milgrom have developed an alternative framework known as modified Newtonian dynamics, or MND. This idea suggests that our understanding of gravity itself is incomplete. especially at the incredibly low accelerations found in the vast emptiness between galaxies. In these extreme environments, gravity might behave differently than the laws laid out by Newton and Einstein predict, creating the illusion of missing mass without any actual matter being there. It's a compelling idea, but even MUND has its own set of challenges and doesn't perfectly explain all the gravitational observations within the dense confines of galaxy clusters. So the mystery only deepens, leaving us with two equally extraordinary possibilities. Either the universe is filled with a mysterious, invisible substance that forms the cosmic bedrock of everything, or our fundamental comprehension of gravity, a force we thought we understood, is fundamentally flawed. This isn't just a small gap in our knowledge, it's a chasm at the very heart of physics, and its resolution will undoubtedly rewrite the textbooks for generations to come. But the plot only thickens as we venture further into the supercluster and encounter a mystery of even greater immediacy, one that involves our own galaxy being pulled on a mysterious cosmic current. As we established, the entire Virgo supercluster is in motion, but for a long time, astronomers were utterly baffled about where it was heading. The answer, when it finally came, was both astonishing and deeply puzzling. Our entire local group of galaxies, along with thousands of others, is being pulled toward a specific, immense gravitational focal point located near the Norma cluster, roughly 250 million light-years away. This colossal enigma is known as the Great Attractor. The sheer scale of this force is almost impossible to comprehend. It's orchestrating the motion of billions of stars across an unfathomable volume of space, with our Milky Way rushing toward it at an incredible speed of over 600 kilometers per second. There's just one monumental problem. The precise location of this attractor lies directly behind the plane of our own galaxy, in a region astronomers call the zone of avoidance. This is the thickest, most crowded part of the Milky Way, where vast clouds of interstellar gas and dust block almost all visible light from the universe beyond. It's like trying to find the source of a powerful magnet that's pulling on you, but it's hidden behind a dense, impenetrable brick wall. For decades, this cosmic blind spot kept the Great Attractor's true nature completely secret. The breakthrough came when we learned to see the universe in a different light, literally. By employing telescopes that peer into the infrared and X-ray spectrums, which can pierce through that obscuring dust, we've begun to lift the veil. What these observations revealed was not a single gargantuan object, but an even more complex and massive confluence of structure than initially imagined. The attractor appears to be the heart of a staggeringly large supercluster of galaxies, now called the Laniakea Supercluster, of which our Virgo Supercluster is merely a featherweight appendage. Yet, even with this clearer picture, the mystery is far from solved. While we can now see the immense collection of galaxies in that region, their combined mass still doesn't fully account for the terrifying gravitational strength we observe. This has led scientists to a compelling and somewhat unsettling conclusion. The Great Attractor itself might not be the final destination, but merely a waypoint on a far grander cosmic journey. The gravitational tug we feel could be driven by something even more immense lying beyond it, an entity known as the Shapley Attractor, the largest concentration of matter in our observable universe. So the Great Attractor may be both a destination and a signpost, a symptom of a deeper gravitational hierarchy that we are only beginning to map. It serves as a humbling reminder that even as we solve one cosmic riddle, we often find it is connected to a larger, more profound puzzle, pulling us ever deeper into the unknown. Moving from the immense gravitational mysteries that shape our supercluster, we arrive at a puzzle unfolding on a slightly smaller, yet equally baffling scale. Nestled at the heart of the Virgo supercluster itself is the Virgo cluster, a dense metropolis of over 2,000 galaxies. In such a crowded urban cosmic environment, conventional astronomy tells us we should expect a certain kind of behavior. The space between galaxies here isn't empty, It's filled with a superheated plasma known as the intracluster medium, a brutal environment that acts like a scorching, high-pressure wind. When a galaxy falls into this dense core, this intense intergalactic wind should violently strip away its cool gas, the very raw material needed to birth new stars. According to our models, this process, called ram pressure stripping, should quickly strangle star formation, leaving behind quiescent, red and dead galaxies that slowly fade away. This is the expected fate for most galaxies in a cluster's violent core, but the universe, it seems, loves to defy expectations. Recent observations from telescopes like the Hubble and the Very Large Array have revealed a population of galaxies right in the thick of this cosmic fray that are not dying quietly. Instead, they are bursting with vibrant, vigorous new life, exhibiting massive waves of star formation that light them up in the infrared spectrum. They are cosmic rebels, forming stars at a rate that completely contradicts our predictions for such a hostile neighborhood. It's the equivalent of finding a lush, thriving garden growing with explosive vitality in the middle of a scorching desert. How is this even possible? The answer appears to lie in the very process we thought would kill them. For some of these galaxies, the immense pressure of the intracluster medium might actually be compressing their remaining reservoirs of gas, triggering a final, glorious burst of star formation, a sort of stellar last stand before the galaxy is ultimately quenched. In other cases, the violence of the cluster environment might be causing galactic collisions and mergers, even in this vast space, funneling huge amounts of gas into the hearts of galaxies and igniting star-forming frenzy. Then there are the so-called jellyfish galaxies, easily identified by their long, streaming tails of gas that are being brutally torn away by ram pressure. Paradoxically, even as they are being actively disassembled, star formation is often rampant within these very tails as the stripped gas condenses and collapses into new stars. It's a beautiful and violent paradox, the mechanism of destruction simultaneously becoming the catalyst for creation. This forces a profound revision of our understanding of galactic life cycles. Galaxies are not simply passive victims of their environment. They are dynamic, resilient entities that can sometimes harness even the most extreme forces to spark new life. The Virgo cluster serves as a real-time laboratory, showing us that the story of a galaxy is far more complex and dramatic than we ever imagined. A continuous tug of war between the forces of destruction and the persistent, undeniable urge to create. But if the violent core of the Virgo cluster shows us galaxies fighting for survival, then the strange behavior of dark matter within them reveals a puzzle on an even more fundamental level. We've established that this invisible substance is the cosmic scaffolding, but what happens when we look closely and find that this scaffolding is built in ways that defy our best blueprints? For decades, the prevailing model of cosmology, known as lambda cold dark matter, has been remarkably successful. It describes a universe dominated by dark energy and populated by slow-moving or cold dark matter particles. This model beautifully predicts the large-scale structure of the universe, the vast cosmic web of filaments and voids that we observe. Within this framework, supercomputer simulations create intricate virtual universes, showing how dark matter should coalesce into smooth, predictable halos around galaxies. These halos are supposed to be dense at the center and become progressively more diffuse as you move outward, following a specific and universal density profile. Yet, when astronomers began to map the actual distribution of dark matter in real galaxies, primarily by meticulously tracking the motions of stars and gas clouds within them, they started finding glaring discrepancies. The dark matter wasn't always behaving as the simulations dictated. Some galaxies appeared to have dark matter halos that were far too puffy and spread out, their densities much lower than expected in their central regions. Others seemed to have dark matter that was concentrated in bizarre, lopsided configurations or even in faint, ring-like structures surrounding the galaxy. It's the cosmic equivalent of expecting a perfectly smooth, round ball of dough, only to find it's full of unexpected lumps, holes, and irregular shapes. One of the most famous examples of this is the phenomenon known as core cusp. Simulations predict that dark matter should form a steep cusp, a sharp peak in density at the very center of a galaxy. However, observations of many dwarf galaxies, which are thought to be dominated by dark matter, consistently show a much flatter core instead. This isn't just a minor accounting error, it's a direct challenge to the properties we've assumed for dark matter itself. The implications of these anomalies are profound. They suggest that our understanding of how dark matter interacts, either with itself or with the normal forces of the universe, might be incomplete. Perhaps dark matter isn't entirely cold and collisionless. Maybe some of it is ever so slightly warm, meaning the particles move at a fraction of the speed of light, which would prevent them from clumping together on the smallest scales, thereby explaining those fluffier cores. Or perhaps dark matter particles can interact with each other through some unknown force, creating friction that smooths out the central cusps into cores. Some of the most intriguing, albeit speculative, ideas even propose that dark matter could be subject to a type of dark electromagnetism, allowing it to form those intricate ring-like structures we sometimes glimpse. Each of these possibilities points toward a dark sector that is far more complex and rich than the simple, inert substance we've imagined for so long. Every anomalous galaxy we find is like a new piece of evidence in a grand cosmic trial, forcing us to question the very nature of the majority of matter in the universe and pushing our models to their breaking point. And just when we thought we had a handle on the strange ways dark matter and galaxies can interact, the universe presents us with an even more ethereal and contradictory class of objects. Scattered throughout the Virgo Supercluster are enigmatic cosmic phantoms known as ultra-diffuse galaxies. Imagine an island universe the size of our own Milky Way, but one that has somehow failed to build itself properly. It contains only about 1% of the stars, leaving it so incredibly faint and gossamer thin that it barely registers against the blackness of space. For a long time, these ghostly giants were nearly impossible to detect, their light so spread out it simply melded into the background glow of the night sky. It was only with the advent of our most powerful digital sky surveys and sophisticated light filtering techniques that we began to pull them into focus, revealing a population of galaxies that should not, by our current understanding, even exist. What makes them truly extraordinary is how they completely shatter one of astronomy's most trusted rules, the mass-metallicity relation. This principle is a cornerstone of galactic evolution, stating that the more massive a galaxy is, the more metals, which in astronomy means any element heavier than hydrogen and helium it should contain. This makes perfect sense. Bigger galaxies have stronger gravity to hold onto the heavy elements forged in supernova explosions, and they've typically undergone more generations of star formation to enrich their gas. But ultra-diffuse galaxies are the ultimate rule breakers. They possess the mass and size of a full-fledged galaxy, yet their stellar populations are incredibly metal-poor, resembling the pristine, ancient conditions of the early universe. It's like finding a sprawling, modern metropolis that somehow functions with only the technology and materials of the Stone Age. The plot twists even further when we try to pin down what provides their mass. Some of these ghostly galaxies, like the famous Dragonfly 44, are staggeringly rich in dark matter. Measurements show that despite having almost no stars, their mass is almost entirely composed of this invisible substance, making them effectively invisible dark matter fortresses. They are the answer to a question we didn't think to ask. Can a galaxy be almost all halo and no disk? Conversely, other ultra-diffuse galaxies, like those found near the center of the Virgo cluster, appear to be almost completely devoid of dark matter. This second group is arguably even more perplexing, as our entire model of galaxy formation is predicated on the idea that galaxies form first within halos of dark matter. A galaxy without dark matter is like a whirlpool without water. It shouldn't be able to form or hold itself together in the first place. So how do we solve this bizarre duality? One compelling theory for the dark matter-rich phantoms is that they are failed galaxies. Perhaps they formed very early on within unusually massive and dense dark matter clumps, but their gas was somehow prevented from cooling and collapsing to form stars. A nearby quasar's radiation or the heat from a nearby galactic collision might have sterilized them, leaving their vast dark matter halos intact but starved of stellar light. For the dark matter-poor galaxies, the explanation might be even more violent. Their journey through the dense core of the Virgo cluster could have subjected them to extreme tidal stripping, a gravitational pummeling that ripped away not only their stars and gas but also their dark matter halos, leaving behind a scattered, skeletal remnant of what was once a normal galaxy. These two extreme ends of the spectrum force us to confront the incredible diversity of galactic evolution and acknowledge that the universe has more than one way to build or unbuild an island of stars. This brings us to a related but fundamentally different puzzle, one that challenges our understanding of cosmic structure on the smallest scales. If dark matter is the foundation upon which all galaxies are built, then our best cosmological model provides a very specific recipe for how that construction should unfold. According to the robust simulations of the lambda cold dark matter model, the process is beautifully hierarchical. Vast halos of dark matter are the first to condense out of the early universe, and then smaller clumps of dark matter, known as subhalos, are drawn in by gravity to orbit within these larger structures. The model makes a clear and testable prediction. For a giant spiral galaxy like our own Milky Way, there should be a veritable swarm of these dark matter subhalos surrounding it, perhaps even thousands of them. And crucially, a significant number of these subhalos should be massive enough to have pulled in gas and ignited star formation, becoming the dwarf satellite galaxies we can actually observe. However, when we look out at the real universe, particularly at the galaxies within our local supercluster, the numbers tell a very different and confusing story. We simply do not see the predicted multitude of dwarf satellites. Our Milky Way has about 60 known satellites, and our nearest large galactic neighbor, Andromeda, has a similar number. While that might sound like a lot, it is orders of magnitude fewer than what the most sophisticated supercomputer simulations tell us we should be finding. This glaring mismatch between theoretical prediction and observational reality is known as the missing satellites problem, and it has been a persistent thorn in the side of cosmology for decades. So where did all the missing satellites go? Scientists have explored two primary avenues to solve this conundrum. The first possibility is that our observations are simply incomplete. After all, dwarf galaxies are intrinsically faint, and detecting them, especially the smallest and most diffuse ones, is an immense technical challenge. It is entirely plausible that a vast population of these tiny, dark galaxies is lurking just beyond the current limits of our telescopes, hidden in the shadows. In fact, recent surveys like the Dark Energy Survey have begun to find more of these ultra-faint dwarfs, suggesting that we are gradually chipping away at the discrepancy. But many astronomers suspect that even with these new discoveries, we may never find enough to completely close the gap, which leads to the second, more revolutionary possibility. The problem isn't with our eyes, but with our theory. Perhaps the simulations are over-predicting the number of satellites because our understanding of dark matter or the physics of star formation in the early universe is flawed. One compelling solution involves the very nature of the first stars. The earliest generations of stars, known as population 3 stars, are thought to have been incredibly massive, hot, and short-lived. When they exploded as supernova, they would have flooded their tiny host subhalos with intense ultraviolet radiation and powerful winds. This violent feedback could have effectively sterilized the smallest dark matter clumps, blowing out all of their gas and preventing them from ever forming stars, leaving them as completely dark, invisible halos. In this scenario, the satellites aren't actually missing. They're just dark, forever cloaked in shadow because the physics of the early universe prevented them from lighting up. This elegant idea reconciles the theory with the observations, suggesting the dark matter subhalos are all there, just as the model predicts, but the vast majority fail to become galaxies we can see. The Virgo Supercluster, with its dense collection of galaxies, offers a perfect testing ground for these ideas. By studying the satellite populations around galaxies like M87, we can gather more evidence to see if the problem truly is one of observation or a more fundamental issue with our core cosmological model. Each faint, newly discovered dwarf galaxy is a critical data point in this grand investigation, helping us determine whether we need to tweak our understanding of astrophysical feedback or if we are being guided toward a more profound revision of the nature of dark matter itself. While our attention has been focused on the stars and galaxies, some of the most profound mysteries are found in the seemingly empty spaces between them. Drifting through the immense voids of the Virgo Supercluster, astronomers have stumbled upon enormous, isolated clouds of pure hydrogen gas, completely untethered from any visible galaxy. These are not the wispy, diffuse remnants of galactic collisions. These are massive, coherent structures, some containing enough raw material to build entire galaxies worth of stars, yet they float in lonely darkness, refusing to coalesce into the brilliant suns they seem destined to become. Their existence is a direct challenge to our narrative of how structure forms in the universe, presenting us with a population of cosmic orphans whose origins are a complete enigma. The discovery of these clouds was almost as unexpected as the objects themselves. They were found not by optical telescopes searching for starlight, but by radio telescopes tuned to the specific frequency emitted by neutral hydrogen atoms. As this faint radio whisper travels across the universe, it leaves a telltale signature that astronomers can decode, revealing the presence, location, and velocity of this most fundamental building block. When researchers pointed these immense dishes at the gaps between galaxies in the Virgo cluster, they expected to map the faint, tenuous bridges of gas predicted to stretch between gravitationally interacting neighbors. Instead, they found dense, well-defined clouds of hydrogen sitting in splendid isolation, with no visible parent galaxy to explain their presence. It was like hearing the distinct and powerful cry of an infant in an empty room with no one else around for miles. The puzzle only deepens when we consider the physics at play. A cloud of gas this large, left to its own devices in the vacuum of space, should not be able to hold itself together. According to the laws of thermodynamics, it should simply dissipate, its particles drifting apart until the cloud vanishes into the background. The fact that these structures remain coherent for hundreds of millions of years suggests that something invisible must be containing them, acting as a gravitational bottle to hold the gas in place. The most straightforward explanation would be a massive halo of dark matter, a gravitational anchor providing the needed weight to keep the cloud from flying apart. If true, this would be a monumental discovery, a dark matter halo that, for some unknown reason, failed to collect enough gas to form stars, leaving its hydrogen contents visible as a ghostly beacon. This would provide a direct, uncontaminated look at the dark matter scaffolding of the universe, separate from the messy complications of stars and stellar explosions. However, alternative theories are just as compelling. Perhaps these clouds are not primordial structures at all, but the spectacular aftermath of a high-speed galactic collision. When galaxies interact, they can slingshot vast streams of gas out into intergalactic space through immense gravitational tides. Another violent possibility is that they are the remnants of a galaxy that has been completely stripped bare by its passage through the dense core of the Virgo cluster. The brutal process of ram pressure stripping could have torn away every last star and shred of identity, leaving behind only a ragged cloud of gas as its sole tombstone. There's even a more exotic idea that these clouds are the seeds of future galaxies, vast reservoirs of pristine fuel that are only now, after billions of years of drifting, beginning to feel the gravitational tug that will one day pull them into a new cosmic structure. Each hypothesis paints a dramatically different picture of the cloud's life story, from tragic relic to promising precursor. Their enduring mystery serves as a powerful reminder that the universe is still full of basic, fundamental questions we cannot answer. We have mapped the large-scale structure of the cosmos and peered back to the first moments of the Big Bang, yet we are still discovering entirely new classes of objects in our own intergalactic backyard, objects that defy simple classification. These hydrogen clouds are more than just celestial curiosities. They are potential keys to understanding the intricate dance between dark and visible matter, the violent history of galaxy clusters, and the ultimate fate of the raw material that births stars. They represent a universe that is still capable of surprising us with its simplicity and its complexity, floating in the darkness as silent, enduring questions. Now, if the invisible cosmic orphans of rogue hydrogen clouds challenge our ideas of structure, then the very method we use to map that structure is itself the subject of one of the most heated and controversial debates in modern astronomy. To understand the universe's scale, we rely on a fundamental tool called redshift. As light from a distant galaxy travels across the expanding universe, its wavelengths are stretched, shifting toward the red end of the spectrum. This redshift is directly related to the galaxy's velocity away from us, and thanks to Hubble's law, we can convert that velocity into a distance. It's the primary ruler we use to measure the cosmos, and it underpins our entire three-dimensional map of the Virgo Supercluster and everything beyond it. We've built our understanding of an expanding, evolving universe upon the bedrock assumption that redshift is a smooth and reliable indicator of cosmic distance. But what if that ruler has hidden markings we never noticed? Beginning in the late 1970s and continuing for decades, astronomer William Tift, and later others like Halton Arp, published a series of astonishing and deeply contentious claims. Their meticulous analysis of galaxy redshifts, particularly within nearby groups and clusters like Virgo, suggested that these values were not smoothly distributed. Instead, they appeared to be quantized, clustering around specific, preferred values with empty gaps in between. It was as if the universe's expansion wasn't a smooth acceleration on a continuous freeway, but rather a car that could only occupy specific, discrete speed limits, hopping from one to another without traveling at the speeds in between. If true, this would be nothing short of revolutionary, implying that redshift is not solely a product of universal expansion, but also contains a component that is intrinsic to the galaxy itself, a fundamental property that can only exist at certain discrete levels. The implications of such a discovery would send shockwaves through the entire field of cosmology. It would suggest that galaxies are born with a set of inherent quantum-like states, an idea that sounds more like subatomic physics than astronomy. This could point toward large-scale structure formation mechanisms that are completely unaccounted for in our current models, perhaps even hinting at a deeper, underlying order to the cosmos that we have yet to comprehend. For a time, the controversy raged, splitting the astronomical community. Mainstream cosmologists largely dismissed the findings, attributing them to selection biases in the data, statistical flukes, or subtle errors in measurement technique. The prevailing lambda cold dark matter model, which so successfully describes the smooth, web-like structure of the universe, had no room for such quantization. It became a textbook example of an extraordinary claim requiring extraordinary evidence that the majority of the scientific community felt was never convincingly provided. Yet, like a stubborn specter, the idea has never fully gone away. Modern surveys with vastly larger datasets occasionally still report strange, periodic patterns in the distribution of galaxies or quasars on truly enormous scales, echoes of that original controversial claim. The debate now is less about the original specific claims and more about what such persistent anomalies could mean for our overall understanding. Could there be a subtle, yet to be understood systematic error affecting all our measurements? Or are we being pushed, however reluctantly, toward considering that our fundamental assumptions about the nature of space, time, and expansion might require some adjustment? The redshift quantization controversy serves as a crucial reminder of the nature of scientific progress. It highlights the tension between bold, paradigm-challenging ideas and the rigorous, often painstakingly slow process of verification and consensus. Even if the original claim is ultimately proven incorrect, the debate itself forces us to sharpen our tools, question our axioms, and remain open to the possibility that our most trusted cosmic ruler might still have a few secrets left to reveal. While we often picture galaxies as isolated islands of light separated by vast oceans of empty blackness, the space within a dense cluster like Virgo is actually filled with a faint, omnipresent glow. This ethereal luminescence, known as intracluster light, is the collective starlight of billions of stars that have been violently evicted from their home galaxies and now drift forever in the intergalactic void. For a long time, this ghostly background was considered little more than cosmic pollution, the predictable and rather dull aftermath of galaxies brushing past one another in the crowded cluster environment. The prevailing theory was straightforward. As galaxies interact, their gravitational tide should pull out long, faint streams of stars, which would then slowly homogenize into a smooth, diffuse cloud of light evenly distributed throughout the cluster's core. But when astronomers finally trained their most sensitive instruments, like the Hubble Space Telescope, to meticulously map this faint glow in the Virgo cluster, they found a reality that was far more complex and mysterious. Instead of a smooth, uniform fog, the intracluster light is organized into intricate and colossal structures, luminous rivers, plumes, and bridges that stretch for millions of light years, weaving between the galaxies like cosmic spiderwebs. These are not the relaxed, well-mixed remnants of ancient collisions. They appear dynamic, almost fresh, telling a story of recent and immense violence that our simulations struggle to replicate. The sheer brightness and complexity of these structures suggest a rate of stellar stripping that is far more efficient and dramatic than our models of galaxy interactions predict. It's as if we've been modeling car fender benders, but the universe is actually hosting demolition derbies. The plot thickened even further when spectrographs analyzed the chemical makeup of this orphan starlight. Stars hold a forensic record of their origins in their atmospheres. Those born in the rich, metal-filled environments of a galaxy's bustling center have a different chemical signature than those from the quieter, metal-poor outskirts. Astronomers expected the intracluster light to be a well-mixed soup, averaging out these differences into a bland, homogeneous blend. What they found was utterly surprising. The light showed a pronounced overabundance of metals, meaning it is dominated by stars that were born in the inner, denser regions of galaxies. This is a profound clue. It suggests that the process of tearing stars away from their homes is not random. It seems to be preferentially ejecting stars from the very hearts of galaxies. This is the opposite of what you might expect if galaxies were simply being gently pulled apart by tides. It points to a mechanism that is violently and efficiently digging deep into a galaxy's core to yank out its stars. So what incredibly powerful force is capable of doing this? The prime suspect is a process called tidal shocking. When a galaxy plunges at high speed through the dense core of a cluster, it doesn't experience a slow, steady pull. Instead, it encounters a sudden and immense gravitational shock, a violent jolt from the combined gravity of all the dark matter, galaxies, and hot gas in the cluster's center. This shock can resonate through the entire galaxy like striking a bell, and the resulting vibrations can eject huge swaths of stars from the inner regions in one catastrophic event. This could explain both the lumpy, complex structures we see and their metal-rich composition. Another fascinating possibility involves the gravitational chaos caused by giant supermassive black holes. When two galaxies merge, their central black holes eventually sink to the new core and can form a binary pair. As they orbit, they can act as a gravitational slingshot, flinging legions of surrounding stars out of the galaxy entirely with incredible force. This theoretical process could be a stellar factory for the intracluster medium, violently scattering a galaxy's core population into the void. This enigmatic glow is far more than just lost starlight. It is a brilliant, if faint, archive of the cluster's most violent history. By reading its intricate structures and its chemical fingerprints, we are beginning to understand that the evolution of galaxy clusters is a far more aggressive and dramatic process than we ever imagined. The intracluster light reveals that galaxies are not just gently merging, they are being actively and brutally dismantled, their very hearts scattered across the darkness, painting a ghostly picture of cosmic violence on the largest scale. But the mysteries of stripped stars and orphaned light are just one facet of the Virgo cluster's violent nature. To truly understand the forces at play, we must peer into the darkest hearts of its most compact stellar cities, the ancient globular clusters and the faint dwarf galaxies that orbit larger hosts. For decades, our models of these dense environments were built on a clear foundation. They are simple, ancient systems where stellar dynamics are well understood. The immense gravitational pull at their cores should have long ago ejected any heavy, sinking black holes through a process called dynamical friction, effectively cleaning them out of such massive, dark remnants. Any black holes that managed to form would be the relatively small stellar mass variety, the corpses of massive stars. This tidy picture was completely upended when the Laser Interferometer Gravitational Wave Observatory, or LIGO, began its historic work. As it listened for the faint ripples in space-time caused by cataclysmic cosmic events, it started hearing the signatures of black holes merging. But many of these black holes were not the expected 20 or 30 solar mass objects. They were monsters weighing in at 50, 60, even 80 times the mass of our Sun. Even more puzzling was the location suggested for some of these mergers, the incredibly dense environments of globular clusters. How could black holes this massive not only form but also survive and find partners in an environment that was supposed to be hostile to their very existence? The data was screaming that our understanding was critically flawed. This triggered a frantic re-examination of these old stellar systems, and what astronomers found within our own supercluster was nothing short of astonishing. Using indirect methods to probe the gravitational heart of these clusters, such as meticulously tracking the motions of stars at their very centers, researchers began to find evidence for missing mass that could only be explained by the presence of not one, but multiple black holes. Some clusters appear to be harboring a whole population of stellar mass black holes that have somehow avoided being ejected. They may be locked in complex gravitational dances, occasionally pairing up and merging to create the massive objects LIGO detects. This suggests that globular clusters are not the serene retirement homes for stars we thought they were, but are instead dynamic arenas where black holes can form, survive, and collide. The surprises don't stop there. In the faint dwarf galaxies that dot the Virgo Supercluster, astronomers have made an even more perplexing discovery: the presence of supermassive black holes that have no right being there. According to the well-established scaling relations that govern most galaxies, the mass of a galaxy's central black hole is directly proportional to the mass of its central bulge of stars. Giant elliptical galaxies host billion solar mass black holes. A small dwarf galaxy should have a correspondingly small central black hole, perhaps only a few thousand solar masses. Yet, observations have revealed that many dwarf galaxies possess monstrously large black holes for their size, with masses that completely defy this cosmic rulebook. It's the equivalent of finding a small suburban home with a power plant in its basement that could energize an entire metropolis. How did these dwarfs acquire such oversized engines? One possibility is that they are the surviving primitive building blocks of larger galaxies, the ancient leftovers from the early universe that never merged into bigger structures. If that's the case, their black holes could be some of the very first seeds that formed pristine relics from a time when the rules of black hole genesis were completely different. Another, more violent theory is that these black holes are not native to the dwarfs at all, but were instead stolen. During a close encounter or a merger between galaxies, a black hole could have been gravitationally ripped from its original host and captured by a much smaller dwarf, leaving it with an impossibly large and powerful heart. This would make these faint galaxies the unlikely thieves of cosmic giants. Each of these discoveries forces a dramatic rethink of how black holes are born, how they grow, and the role they play in shaping the environments around them, from the very largest scales down to the most compact. Drifting in the vast intergalactic space within the Leo group of galaxies, part of our Virgo Supercluster neighborhood, lies a structure so immense and perplexing it has captivated and confounded astronomers since its discovery. Known as the Leo Ring, it is a colossal, necklace-like loop of primordial hydrogen gas, stretching for nearly 200,000 light-years across. This isn't a faint, wispy cloud. It contains enough raw material to forge hundreds of millions of stars like our Sun, a veritable treasure trove of cosmic building blocks. Yet, despite its staggering abundance, this vast reservoir of gas remains almost completely dark, refusing to collapse and ignite into the brilliant fires of new suns. Its sheer scale and its stubborn refusal to conform to our expectations present a fundamental riddle about the origins of structure in the universe, forcing us to choose between two radically different stories of its birth. The most awe-inspiring possibility is that the Leo Ring is a pristine relic, a fossil from the very dawn of time. In this scenario, the ring is a leftover pocket of the primordial gas that filled the universe after the Big Bang, a cloud of pure hydrogen and helium that has somehow managed to avoid falling into a galaxy for over 13 billion years. It would be a perfectly preserved time capsule from the ancient cosmos, a sample of the raw material from which the very first stars and galaxies were forged, completely uncontaminated by the heavy elements later created in stellar furnaces. The existence of such a structure would be nothing short of miraculous. To survive for so long, it would need a stable, quiet orbit, perfectly balanced within the gravitational tug of war between the galaxies of the Leo group, somehow evading the violent collisions and disruptive forces that have stirred up the rest of the universe. Finding this ring would be like discovering a perfectly preserved, bubble-wrapped artifact from a long-lost civilization, completely untouched by the ravages of time. However, the universe is rarely so gentle, which leads to the competing and more violent theory for the ring's origin. Perhaps this beautiful, symmetrical loop is not a primordial fossil at all, but the spectacular aftermath of a cataclysmic collision, a cosmic car crash of unimaginable proportions. The theory posits that billions of years ago, two large galaxies had an incredibly close, high-speed encounter. During this gravitational dance, immense tidal forces could have ripped vast streams of gas from their outer disks, flinging it out into intergalactic space. The specific geometry of the collision could have sent this gas into a stable, ring-like orbit where it has been circling ever since. This tidal debris model elegantly explains the ring's coherent, organized structure, something that can be difficult to account for with the primordial theory. It transforms the ring from a passive relic into a dynamic scar, a permanent record of a violent event that occurred in the distant past. So how do we decide between these two compelling narratives? Astronomers turn to forensic chemistry, analyzing the light that filters through the ring to search for the faintest chemical fingerprints. The key clue lies in the presence of heavy elements which astronomers call metals. A truly primordial cloud would be composed almost exclusively of hydrogen and helium, the elements forged in the Big Bang. It would be metal-free. If, however, the ring was torn from the disks of evolved galaxies, it should contain at least trace amounts of those heavier elements, the carbon, oxygen, and iron that are forged in stars and scattered by supernova. For years, the evidence was frustratingly inconclusive. Some observations suggested the gas was pristine, supporting the relic theory. Others hinted at faint metal lines pointing toward a tidal origin. Recent studies with powerful instruments have begun to tip the scales. Extremely deep spectroscopic observations have now detected the faint signature of heavy elements within the ring's gas. This crucial piece of evidence strongly suggests the material has been processed through stars, making the tidal debris model the leading explanation. The most likely culprits for the colossal collision are the two large galaxies that sit near the ring's center, NGC 3384 and NGC 3389. Their positions and motions are consistent with an ancient grazing encounter that could have produced just such a magnificent loop of displaced gas. This doesn't entirely solve the puzzle, though. The ring's sheer mass and its enduring, stable structure remain challenging to model perfectly, suggesting the precise details of the collision were extraordinarily unique. The Leo ring stands as a breathtaking example of the universe's creative destruction, a beautiful remnant of ancient violence that continues to challenge our models and deepen our appreciation for the dynamic history hidden within the quiet spaces between the stars. While dark matter provides the overarching framework for galactic behavior, its application is not always a perfect fit, and certain galaxies within the Virgo Supercluster present rotation patterns that defy even this mysterious model. Think of a galaxy's rotation curve as its unique fingerprint, a graph that plots the orbital speed of stars and gas against their distance from the galactic center. According to Kepler's laws, which work perfectly for planets in our solar system, we would expect these speeds to drop off dramatically as you move further out from the gravitational pull of the central mass. But for decades, we've known this isn't the case. Instead of falling, the rotation curves of spiral galaxies remain flat far out into their outskirts, which was the original and most powerful evidence for the existence of dark matter halos. These halos provide the extra gravitational glue to keep those outer stars whipping around at high speed. However, when astronomers train their most sensitive radio telescopes on individual galaxies within Virgo, they find that this story is often far messier and more intriguing than the simple, smooth curve the dark matter model predicts. Some galaxies exhibit what can only be described as a sudden kink in their rotation curve, a sharp, unexpected transition where the velocity of the gas drops or rises precipitously over a very short distance. It's the cosmic equivalent of driving down a highway at a steady 60 miles per hour and then, for no apparent reason, hitting an invisible wall that instantly slows you to 20, only to speed up again just as abruptly a moment later. This isn't a gentle, gradual change dictated by a smooth dark matter distribution. It's a jarring anomaly that suggests something far more structured or dynamic is at work within the halo itself. Other galaxies within the supercluster present another puzzle, dramatically lopsided rotation. The gas on one side of the galaxy might be orbiting at a significantly different speed than the gas at the same distance on the opposite side, creating an asymmetrical velocity field. This is a profound violation of the basic assumption of a tranquil, equilibrium state. A smooth, spherical halo of dark matter should not produce such a stark imbalance. Gravity is, after all, an equal opportunity force. This asymmetry points a finger toward a recent and violent gravitational disturbance. The culprit could be a close encounter with another galaxy, a near miss that gravitationally shocked the dark matter halo, stirring it up and creating dense lumps and wakes within it. These irregularities in the invisible scaffolding would then tug on the visible gas, creating the unbalanced rotation speeds we observe. Alternatively, the galaxy might be actively accreting a massive cloud of intergalactic gas, a process that could impart a directional pull on one side of the disk, throwing its elegant rotation into temporary chaos. Perhaps the most tantalizing possibility is that these anomalous curves are giving us our first indirect glimpse of the true nature of dark matter. The standard model assumes dark matter is cold and collisionless, meaning particles pass right through each other without interaction. But what if that's not entirely true? If dark matter particles had even a tiny ability to interact with each other, through some unknown dark force they could exhibit fluid-like behaviors, forming waves, shocks, and complex substructures within the halo. A sharp kink in a rotation curve could be the signature of a propagating density wave within this dark fluid, while an asymmetry could indicate a large, coherent clump of self-interacting dark matter. Each anomalous galaxy becomes a unique natural experiment, a laboratory for testing the properties of the universe's dominant form of matter. These aren't failures of the dark matter paradigm. They are its most exciting and cutting edge, providing the crucial clues that will help us move from simply knowing dark matter exists to finally understanding what it actually is. This peculiar motion of our entire galactic neighborhood is one of the most profound and humbling puzzles in all of cosmology because it fundamentally asks a simple question: what in the universe is powerful enough to pull us? We are not stationary observers. Our entire local group of galaxies, including the Milky Way and Andromeda, is caught in a vast cosmic current, rushing through space at a staggering 600 kilometers per second relative to the oldest light we can see, the cosmic microwave background. To put that immense speed into perspective, we are moving fast enough to travel from Earth to the Moon in under 11 minutes. This isn't a random drift, it's a directed, purposeful flow, and for decades, its origin has been one of astronomy's greatest detective stories. The cosmic microwave background, or CMB, is the remnant glow from the Big Bang, and it fills the entire universe with an almost perfectly uniform temperature. However, due to our motion through space, this radiation appears slightly warmer in the direction we're heading and slightly cooler in the direction we're leaving behind, an effect known as dipole anisotropy. By measuring this temperature difference, we can calculate our precise velocity relative to this fundamental rest frame of the cosmos. The result was that astonishing 600 km/s figure. But velocity alone isn't the mystery, it's the acceleration required to achieve it. An object doesn't just reach such an incredible speed on its own. It must be pulled by gravity, and a lot of it. The hunt was on to find the source of this immense gravitational tug. For a long time, the prime suspect was the same colossal structure we discussed earlier, the Great Attractor. This immense concentration of mass near the Norma cluster seemed perfectly positioned to explain our motion. It was a gravitational focal point of epic proportions, and for a while it appeared the case was closed. But as our maps of the large-scale structure of the universe improved, particularly with surveys that could peer through the zone of avoidance, astronomers made a startling realization. The combined gravitational pull of the Great Attractor and all the other known superclusters in our vicinity, including the massive Perseus-Pisces supercluster and our own Virgo supercluster, still couldn't account for the full strength of our motion. There was a significant portion of our velocity that remained unexplained. We were being pulled by something even more immense, something lying beyond the Great Attractor. This revelation pointed the finger toward a truly gargantuan structure known as the Shapley supercluster, the single largest concentration of matter in the observable universe. Located over 650 million light-years away, Shapley is a staggering confluence of dozens of rich galaxy clusters, a gravitational behemoth whose collective pull might indeed be the dominant force behind our peculiar motion. The idea is that we are caught in a vast cosmic river, a flow that begins with the pull of Shapley, is channeled and amplified by the Great Attractor and sweeps up our local group in its current. This model, known as bulk flow, suggests that enormous volumes of space are moving together coherently under the influence of these distant, immense mass concentrations. However, even this grand explanation has recently encountered challenges. Some ultra-precise measurements of the cosmic flow suggest that the observed motion might be slightly larger than what the combined pull of Shapley and other known structures can produce. This has led to a fascinating and controversial possibility. What if there is even more mass out there beyond the horizon of what we've currently mapped? The existence of previously unknown superclusters or immense cosmic voids with a gravitational repulsion effect could theoretically account for this discrepancy. It forces us to confront the possibility that we are still missing a major piece of the cosmic cartography puzzle, that the largest structures influencing our fate have yet to be discovered. This peculiar motion is more than just a curiosity. It is a direct measurement of the gravitational landscape of the entire observable universe, and it tells us that we are but a small leaf caught in a current driven by giants we are only just beginning to see. Moving from the grand gravitational currents that pull entire superclusters, we now tune our instruments to a different wavelength of mystery, one that crackles with enigmatic energy. Across the vast radio spectrum, the Virgo Supercluster is alive with a symphony of invisible signals, and some of them are playing tunes we simply cannot decipher. While many radio emissions have straightforward explanations, the furious spin of pulsars or the fiery jets of active galaxies, others remain utterly perplexing, representing transient whispers and persistent hums with no identifiable source. These mysterious radio sources are like finding a powerful, unlicensed broadcast in the middle of a deserted frequency. The signal is clear and strong, but its origin is a complete enigma, hinting at entirely new classes of astronomical objects or phenomena lurking in the darkness. Some of the most baffling signals are the transient ones, sudden, incredibly intense bursts of radio energy that last for mere milliseconds before vanishing without a trace. When these fast radio bursts, or FRB, were first discovered, they sent shockwaves through the astronomical community. Here was an event that could, in 1,000th of a second, release more energy than our sun puts out in 80 years, and then it was just gone. For years, their origins were one of the biggest puzzles in astrophysics. Were they the final death cries of evaporating black holes, the colossal shudders of merging neutron stars? Or something else entirely? The plot thickened dramatically with the discovery of repeating FRBs. Unlike the one-off events, these signals would flash from the same patch of sky again and again, sometimes in erratic patterns, sometimes with an eerie regularity that seemed almost artificial. This repetition immediately ruled out any kind of catastrophic one-time event like a stellar explosion. You can't have a supernova happen twice in the same place. The identification of some repeating FRBs as originating in distant galaxies was a major breakthrough, but it didn't solve the mystery, it only deepened it. We now know these immense energies are being generated far beyond our local supercluster, but the precise engine behind them remains hotly debated. The current best fit model involves a highly magnetized neutron star known as a magnetar. These cosmic powerhouses possess magnetic fields so intense they could strip the information from a credit card from halfway across the solar system. A starquake on the surface of a magnetar, a sudden cracking of its rigid crust, could theoretically unleash a titanic blast of radio waves that we would see as an FRB. This explanation is compelling, but it's not without its problems. The sheer energetic requirements for some of the most powerful bursts push the limits of what we believe even a magnetar is capable of, leaving the door open for more exotic possibilities, like flares from advanced alien civilizations. Ideas scientists take seriously enough to investigate and rule out before moving on to natural explanations. But the transient bursts are only half the story. The radio sky is also dotted with mysterious persistent sources that emit a steady, unwavering radio signal. Yet when astronomers point their most powerful optical telescopes at those exact coordinates, they find nothing. No galaxy, no nebula, not even a faint star. These objects are known as ORCs, or odd radio circles. They appear as giant, faint rings of radio emission, some so large they could encompass entire galaxies, and they defy all attempts at classification. They are not supernova remnants which have a distinct structure and lifespan. They are not the eerie glow of planetary nebulas. They don't match the profile of any known type of galaxy. They are simply there, ghostly, circular enigmas hanging in the void. One leading theory suggests ORCs could be the immense shockwaves from a truly gargantuan event, like the merger of two supermassive black holes millions of years ago. Such a cataclysm would have sent a spherical shockwave of energy expanding outward at nearly the speed of light, and we might be seeing a circular cross-section of that bubble as it stretches across intergalactic space. Another fascinating idea posits that they are the throats of wormholes or the signatures of cosmic strings, hypothetical defects in the fabric of space-time left over from the Big Bang. While these explanations venture into the realm of speculative physics, they highlight just how extraordinary these objects are. They force us to consider that our catalogue of cosmic phenomena is still woefully incomplete, and that the universe is likely filled with processes and objects we haven't even begun to imagine. Each unexplained radio signal, whether a millisecond flash or a million-year-old ring, is a direct message from the unknown, a challenge to our understanding of physics, and a thrilling reminder that the cosmos still holds profound secrets waiting to be decoded. Yet another layer of this grand structural mystery emerges when we shift our focus from the positions of galaxies to the very way they spin. According to our most fundamental cosmological principles, the universe should be isotropic, meaning it has no preferred direction on the largest scales. The initial conditions of the Big Bang set matter expanding in a nearly uniform state, and the tiny quantum fluctuations that seeded all future structure should have been random, leading to galaxies that spin in all possible directions, their rotation axes pointing every which way like a vast, chaotic crowd. Their orientations should be utterly uncorrelated with the large-scale cosmic web they are embedded in. But what if we discovered that this wasn't the case? What if we found evidence that galaxies are, in a sense, all doing the same cosmic dance? This is precisely the controversial claim that has been bubbling at the frontiers of cosmology for years. Several independent studies, using vast datasets from surveys like the Sloan Digital Sky Survey, have reported a bizarre and statistically significant signal. They suggest that the spin axes of spiral galaxies located within the dense filaments of the cosmic web, the very backbone of structures like our Virgo Supercluster, are not randomly oriented. Instead, they appear to show a preference for aligning their rotations either parallel or perpendicular to the filament's long axis. It's as if you dropped countless compass needles onto a map, and instead of pointing north randomly, they all consistently lined up along the roads and rivers. This shouldn't happen in a universe governed by random gravitational growth. It implies that the process of galaxy formation retains a memory of the initial conditions of the universe on a truly colossal scale, a fossilized imprint of the primordial universe that our standard models simply don't predict. The potential mechanisms behind such a coordinated alignment are as profound as they are puzzling. One leading hypothesis reaches back to the very beginning of everything. In the infant universe, vast streams of primordial gas, set in motion by the gravitational pull of dark matter filaments, could have possessed an inherent spin, a specific angular momentum that was inherited from the largest-scale tidal forces in the early cosmos. As this gas flows along these cosmic highways to fuel the growth of galaxies, it may transfer this preferred spin direction to the galaxies themselves, like a river imparting a specific swirl to all the leaves floating on its surface. In this scenario, a galaxy would essentially be born spinning in a way that's dictated by the architecture of the entire filament it calls home. An alternative and even more mind-bending theory involves the influence of magnetic fields on a scale we can barely comprehend. We know that magnetic fields permeate galaxies and galaxy clusters, but could they also be woven through the entire cosmic web? If these fields were exceptionally strong in the early universe, they could have acted like cosmic guides, exerting a force on the ionized gas that was collapsing to form galaxies, nudging their spin axes into alignment with the field lines. This would mean the invisible magnetic architecture of the universe itself is directing the dance of the galaxies. However, this idea is highly speculative, as the origin and sustained strength of such pervasive intergalactic magnetic fields remains one of astronomy's great unsolved problems. The very existence of this phenomenon is hotly debated within the scientific community. Detecting such a subtle correlation requires immense statistical power and incredibly careful analysis to rule out every possible observational bias. Skeptics argue that the reported alignments could be artifacts of how we measure galaxy shapes and rotations, or subtle selection effects in our surveys where we might be unconsciously missing galaxies that don't fit the pattern. The debate is a beautiful example of science in action. An extraordinary claim is met with intense scrutiny, driving the development of better instruments and more rigorous methods to either confirm or refute it. Upcoming missions like the Euclid Space Telescope are designed to map the geometry of the dark universe with unprecedented precision, and they may finally provide the definitive data needed to settle this cosmic controversy. If these alignments are confirmed, we will be forced to radically rewrite our understanding of how angular momentum is distributed across the universe, revealing a level of large-scale coordination in the cosmos that was previously unimaginable. This brings us to a mystery that strikes at a far more fundamental level than the exotic nature of dark matter, a puzzle about the very stuff we're made of. We've spent so much time searching for the 85% of matter that's dark and invisible, but it turns out we've lost track of a shocking amount of the normal, everyday matter, the baryons that make up every star, planet, and person. This is the missing baryon problem, and it's a cosmic accounting error of epic proportions. When cosmologists add up all the normal matter they can see in the universe, all the stars shining in galaxies, all the gas and dust in nebulae, all the planets, the total comes up dramatically short. Based on precise measurements of the cosmic microwave background, which acts as a detailed inventory list from the early universe, we know exactly how much baryonic matter was created in the Big Bang. Yet, when we look around at the present-day universe, especially within our local Virgo Supercluster, we can only account for about half of it. Where did the other half go? It's as if we did a head count at the beginning of a grand cosmic concert, and then halfway through the show, realized half the audience has simply vanished from their seats. The prime suspect in this case isn't some exotic particle. It's a diffuse and incredibly difficult to detect form of ordinary matter known as the warm-hot intergalactic medium, or WIM. Theorized to fill the vast spaces between galaxies and the filaments of the cosmic web, the WIM is not a cold, empty void. It's a sparse soup of gas that has been heated to temperatures between 100,000 and 10 million degrees Kelvin by the immense shockwaves generated by the formation of large-scale structure itself. As vast rivers of matter flowed into the gravitational wells of superclusters like Virgo, this gas was compressed and heated to these tremendous temperatures. At such extreme heat, the gas becomes ionized, meaning its electrons are stripped from their atoms. This makes it virtually invisible to optical telescopes, which rely on seeing the light emitted or absorbed by neutral atoms. It doesn't glow brightly in X-rays like the much hotter gas at the hearts of galaxy clusters, and it's too ionized to emit much radio waves. It's a ghost in the machine, a pervasive background hum of normal matter that has, until recently, slipped through every net we've cast. Proving the existence of the whim and finally balancing the cosmic books has required extraordinary ingenuity. Astronomers have turned to a technique that uses the universe's brightest beacons as backlights, quasars. These immensely powerful active galaxies act like cosmic lighthouses, sending beams of intense radiation across billions of light years. As this light passes through the otherwise invisible filaments of the whim, the highly ionized oxygen and other atoms within it absorb specific wavelengths of the quasar's light. This leaves extremely faint, specific absorption lines in the quasar's spectrum, like a unique chemical fingerprint. Detecting these fingerprints is a Herculean task. The signals are incredibly weak, and distinguishing them from noise requires combining the light from multiple quasars and using the most sensitive spectrographs on the world's largest telescopes. It's painstaking forensic work, but it has begun to pay off. These observations have provided the first compelling evidence that a significant portion of the missing baryons are indeed hiding in this vast hot web of gas. However, even with these detections, the accounting might still not be fully complete. Some models suggest that the whim alone may not contain all of the missing matter, leading to other intriguing possibilities. Could a substantial amount of baryonic matter be locked away in forms we haven't even considered? Perhaps it's tied up in extremely faint, low-surface brightness galaxies that have eluded our surveys, or in a population of rogue planets and brown dwarfs drifting, unseen, in the darkness between the stars. There's even the more speculative idea that some normal matter could have been processed by advanced civilizations on a Kardashev scale, Roman 3 level, though most scientists consider this far less likely than the astrophysical explanations. The hunt for these missing baryons is more than just an exercise in cosmic inventory. It's a critical test of our entire model of the universe's evolution. If we can't find the normal matter we know must be there, it forces us to question whether we truly understand the processes that have shaped the cosmos from its birth to the present day. Every new observation that pins down a few more baryons in the whim is a small victory, slowly closing one of the most fundamental gaps in our understanding of what the universe is actually made of. While we often think of the cosmos in terms of light and gravity, there is another, more energetic messenger constantly bombarding us from the depths of space, the cosmic ray. These are not rays of light, but rather atomic nuclei, mostly protons, that have been accelerated to nearly the speed of light. They are the universe's ultimate natural particle accelerators, and by studying their paths and energies, we can learn about the most violent events in the cosmos. For a long time, it was assumed that the most powerful of these rays, the ones with the highest energies, must originate from far beyond our local supercluster, born in cataclysms like active galactic nuclei in distant voids. The logic was simple. To reach such incredible energies, a particle would need an immense accelerator, and the crowded environment of a supercluster like Virgo, with its tangled magnetic fields, would scatter and slow them down long before they could reach us. This established picture, however, is now being challenged by some truly puzzling data. Detailed mapping by sophisticated observatories like the Pierre Auger Observatory has begun to reveal unexpected concentrations of ultra-high-energy cosmic rays that seem to originate from within the boundaries of the Virgo Supercluster itself. This is the equivalent of detecting the sound of a cannon blast and tracing it not to a distant battlefield, but to a source in your own neighborhood, a place where, according to all our models, such a powerful blast simply shouldn't be possible. The distribution of these particles is also anomalous. Instead of arriving from all directions equally, as one would expect if they were scattered by magnetic fields during their long journey, they show up in faint, clustered patterns that hint at relatively nearby point sources. It's as if we're finding the cosmic ray equivalent of a local factory, producing unimaginably energetic particles right in our cosmic backyard, and we have no idea what the machinery inside looks like. The immediate and most thrilling question is, what could possibly be acting as this local particle accelerator? the known mechanisms within our supercluster seem insufficient for the task. Supernova remnants, the traditional candidates for cosmic ray acceleration, simply don't pack enough punch to explain the very highest energy events we detect. Even the supermassive black hole at the heart of M87, with its famous jet, doesn't quite align with all the observed arrival directions. This forces astronomers to consider far more exotic possibilities. One compelling theory points to large-scale magnetic reconnection events. Imagine the magnetic field lines that permeate the space between galaxies in a cluster like Virgo. These lines can become twisted and stressed over time, and when they finally snap and reconnect, they can release a staggering amount of energy, potentially in a short, violent burst capable of launching particles to near light speed. Another, more speculative idea involves the decay or annihilation of exotic theoretical particles, like those that might make up dark matter. If such particles were to collide and destroy each other, they could release a shower of standard particles, including protons, at tremendously high energies. The implications of solving this mystery are enormous. If the source is a previously unknown type of astrophysical object or a new physical process, it would mean we've been blind to an entire class of cosmic engines operating in plain sight. Confirming a link to dark matter, however, would be a revolutionary breakthrough, providing us with a completely new way to detect and study this elusive substance, not by its gravity, but by the high-energy fallout from its interactions. Every anomalous cosmic ray that strikes our atmosphere is a tiny piece of evidence in this grand investigation, a clue pointing toward physics operating at energy scales we can never hope to replicate on Earth. They are messengers from the most extreme environments in our local universe, carrying encrypted information about forces and processes we are only just beginning to imagine. And now we arrive at one of the most profound and unsettling mysteries in all of modern cosmology, a fundamental crack in the foundation of our understanding that is growing wider with every new observation. It's a problem of measurement, of two different ways of calculating the same number that are yielding two different answers, and it's happening right here in our cosmic backyard. This is the Hubble constant tension, and the Virgo Supercluster is a critical stage where this drama is playing out. The Hubble constant, denoted as H0, is arguably the most important number in cosmology. It represents the current expansion rate of the universe, the speed at which galaxies are receding from us for every megaparsec of distance. Think of it as the master calibration knob for the size, age, and ultimate fate of everything we see. For decades, we've assumed that this number, once precisely pinned down, would be a single, universal truth. The tension arises because we have two supremely confident, yet wildly divergent methods of measuring it. The first approach is what we call the local distance ladder. This is a meticulous, step-by-step process of cosmic cartography that builds out from our local supercluster. Astronomers start by measuring distances to incredibly reliable standard candles within our own galaxy, like Cepheid variable stars, whose known luminosity allows for precise distance calculation. They then use those same Cepheids to calibrate even brighter standard candles, like Type Ia supernova, in nearby galaxies within the Virgo Supercluster and beyond. By observing these brilliant supernovae explode in galaxies at known distances, we can measure their apparent brightness and their redshift, and from that, we can derive a highly precise value for the Hubble constant. This local measurement, championed by projects like the SHOES team, gives us a value of approximately 73 kilometers per second per megaparsec. The second approach looks not at the local universe, but at its very first light. By studying the faint afterglow of the Big Bang, the cosmic microwave background, with exquisite precision using satellites like Planck, we can measure the tiny fluctuations in temperature and density that were imprinted on the infant cosmos. We then run the cosmic film forward using our incredibly successful standard model of cosmology, lambda cold dark matter, which tells us exactly how those tiny ripples should evolve over 13.8 billion years into the vast cosmic web we see today. This model spits out a predicted value for the Hubble constant, and it is unshakably consistent, 67.4 kilometers per second per megaparsec. On the surface, a difference of about 5.6 might not seem like much, but in the realm of precision cosmology, it's a devastating chasm. The error bars on each measurement have been shrunk down so small through painstaking work that they no longer overlap. This isn't a case of sloppy measurements, it's a case of two impeccably crafted keys that simply do not fit the same lock. The implications are staggering. It suggests that something is fundamentally wrong, either with our measurements of the local universe or with our standard model of cosmology itself. This is where the Virgo Supercluster becomes more than just a backdrop. It's an active participant in the mystery. As the largest gravitationally bound structure in our immediate vicinity, it is the primary laboratory for calibrating the local distance ladder. The precise motions of galaxies within Virgo, their peculiar velocities as they flow toward the cluster's center, must be carefully untangled from the overall expansion of the universe to get a clean measurement. Any subtle error in modeling Virgo's complex gravitational field could potentially bias the local H0 value. Yet, after accounting for these factors again and again, the discrepancy persists. This forces us to consider that the problem is not with our maps, but with our model. The lambda-cold dark matter model that works so perfectly for the early universe might be missing a crucial ingredient. Perhaps dark energy is not a constant as we've assumed, but an evolving force that has changed strength over cosmic history. Maybe dark matter possesses some unknown property that causes it to interact in ways we haven't accounted for. Or, most intriguingly, there could be an entirely new type of relativistic particle from the early universe, like a sterile neutrino, that would subtly change how the early universe evolved and thus alter the Planck prediction. Each of these possibilities would constitute a revolution in physics. The Hubble constant tension is no mere academic disagreement. It is a direct challenge, a persistent anomaly that the scientific community can neither ignore nor explain away. It is the universe itself presenting us with a paradox, insisting that for all our knowledge, a profound piece of the cosmic puzzle is still missing. And the answer likely lies hidden in the delicate interplay between the vast, ancient echoes of the Big Bang and the precise motions of galaxies next door. Yet, as if the cosmic ray mystery wasn't enough, yet another invisible force is revealing its own set of surprising rules, weaving through the darkness between galaxies in ways we never anticipated. We tend to think of intergalactic space as the ultimate void, a cold, empty, and fundamentally chaotic expanse where matter is sparse and no meaningful structure can take hold. But it turns out, this vast nothingness is not so formless after all. Radio astronomers, using sophisticated arrays of telescopes to create exquisitely detailed maps of the sky, have begun to detect the faint but unmistakable signature of magnetic fields stretching across millions of light years, linking galaxies and even entire clusters together. This discovery is nothing short of revolutionary. We've long known that magnetic fields exist within galaxies, generated by the churning dynamos of stellar winds and supernova explosions. But the idea that these fields could not only survive in the near-perfect vacuum between galaxies, but also organize themselves into coherent, large-scale structures was considered almost unthinkable. The sheer scale of these magnetic fields is the first jaw-dropping anomaly. They aren't just localized wisps, they are colossal, ordered frameworks that appear to trace the very filaments of the cosmic web itself. Imagine a spiderweb so vast it could connect cities across a continent, but spun from invisible lines of magnetic force instead of silk. These fields exhibit coherence lengths, the distance over which the field maintains a uniform direction that can span entire galaxy clusters. This is a problem because our best theories for how magnetic fields are generated, known as dynamo theories, require a few key ingredients: a dense, electrically conductive fluid like plasma, and some form of rotation or shear to twist and amplify tiny seed fields into organized structures. The space between galaxies possesses almost none of these conditions. The plasma there is incredibly thin, with maybe only 1 atom per cubic meter, and there's no large-scale rotation to speak of. It's like trying to light a bonfire with a single piece of kindling in the middle of a hurricane. The conditions are simply too hostile for the process to work as we understand it. This leaves us with a profound puzzle. How do these immense magnetic structures form, and what is powering them to maintain their coherence against the dissipating forces of the expanding universe? Scientists are exploring 2 broad categories of solutions, each more fascinating than the last. The first idea looks back to the very birth of the cosmos. Perhaps these fields are primordial, imprinted onto the fabric of space-time during a phase transition in the universe's first fraction of a second after the Big Bang. In this scenario, the fields have been stretched and woven into the cosmic web by the expansion of the universe itself, serving as fossil relics from a time of almost unimaginable energy. The second, more dynamic theory proposes that the fields are actually grown from tiny seeds that are later amplified by the incredible violence of the cosmos. As galaxies move through the intergalactic medium, they could act like ships plowing through water, creating wakes and shocks that energize and organize magnetic fields. Even more compelling is the role of active galactic nuclei and their colossal jets. These jets pump not only matter but also magnetic energy into the intracluster medium, potentially inflating giant bubbles of magnetized plasma that can then merge and form a large-scale network. The strength of these fields is the final piece of this puzzle. While they are still far weaker than the magnetic field at the surface of the Earth, they are orders of magnitude stronger than any standard cosmological model predicted for such an environment. This unexpected potency suggests that our understanding of plasma physics on the largest scales is woefully incomplete. There may be unknown amplification mechanisms at work, or perhaps the fields are being sustained by a continuous infusion of energy from the cosmic web itself, as matter flowing along filaments generates currents on a galactic scale. Whatever the explanation, the existence of these magnetic architectures forces us to revise our picture of the so-called empty spaces between galaxies. They are not passive voids but active participants in the cosmic drama, structured by invisible forces that can guide the motion of charged particles, influence the evolution of galaxies, and perhaps even hold clues to the fundamental laws that govern the entire universe. Yet another profound contradiction emerges when we shift our focus from the grand scale of superclusters down to the intimate dance of the smallest galaxies around their hosts. For decades, our most sophisticated supercomputer simulations of a dark matter-dominated universe have painted a very specific picture of how satellite galaxies should behave. According to the lambda-cold dark matter model, these dwarf galaxies are the visible traces of countless smaller dark matter subhalos. They should be swarming around their host galaxy like bees around a hive, orbiting in a vast spherical cloud from all directions. Their distribution should be isotropic, random, and even, a chaotic yet beautiful testament to the random gravitational tumbles of the early universe. This prediction is not a minor detail. It is a fundamental outcome of our core cosmological model. But when astronomers began to meticulously map the real satellites around our nearest large galactic neighbor, Andromeda, they found something that sent a shockwave through the field of cosmology. Instead of a sprawling, three-dimensional swarm, a significant number of Andromeda's dwarf galaxies were arranged with an eerie precision, orbiting in an immense, thin, and incredibly flat plane that slices through the host galaxy. This wasn't a slight statistical clustering. It was a highly structured, rotating disk of satellites, a vast celestial carousel that should not, according to our best simulations, exist. The discovery was so startling that it was initially met with deep skepticism, attributed to a trick of perspective or an observational fluke. However, further incredibly precise measurements from surveys like the Pan-Andromeda Archaeological Survey have only solidified the finding. The plane is real, it's dynamically coherent, and it represents a direct challenge to the very foundations of how we believe galaxies form. The problem only deepens when we realize this isn't unique to Andromeda. Evidence suggests that our own Milky Way satellites might also be arranged in a similar, though less pronounced, planar structure. This means the anomaly isn't a one-off cosmic oddity. It appears to be a feature of galaxy formation, a feature that our premier model of the universe fails to predict. So how do we solve this glaring contradiction between theory and observation? Astronomers have been grappling with two broad classes of solutions, each with monumental implications. The first possibility is that the problem lies not with dark matter itself, but with our understanding of the gas physics and feedback processes that govern the visible universe. Perhaps the plane is a temporary structure, a fossil of the recent accretion of a group of dwarf galaxies that fell into Andromeda together along a cosmic filament. In this group-in-foul scenario, the satellites haven't had enough time to be scattered into a more random distribution by gravitational interactions. While this is a compelling idea, many detailed simulations show that such a thin, rotating plane would be dynamically unstable and should dissolve over a relatively short cosmic timescale, making its continued existence today highly unlikely. The second and far more radical possibility is that the problem points to a flaw in our understanding of dark matter or gravity. This has led to a resurgence of interest in alternative models, particularly modified Newtonian dynamics or MON. Interestingly, MON naturally predicts that satellite galaxies will tend to align with the gravitational field of their host, potentially forming precisely these kinds of planar structures. For proponents of MOND, the satellite planes are not a problem at all, but a successful prediction that the standard model fails to make. However, MOND has its own significant challenges, particularly in explaining the dynamics of entire galaxy clusters without invoking some form of dark matter. Another intriguing idea within the standard model involves the concept of dark matter streams. It's possible that the dark matter halo itself is not a smooth, featureless cloud, but is instead laced with dense, flowing rivers of dark matter left over from its assembly. Satellites forming within or captured by these streams would naturally be channeled into coherent planes, their motions dictated by the invisible infrastructure of the halo itself. The satellite plane problem is more than just an academic puzzle. It is a direct observational test that is forcing a critical re-evaluation of our most fundamental assumptions. It demonstrates that even in our local cosmic neighborhood, the universe retains the capacity to surprise us, presenting structures that challenge our deepest theories and guide us toward a more complete understanding of the invisible forces that sculpt the cosmos. Racing through the immense voids between galaxies, far above and below the starry disks we're familiar with, are enigmatic ghosts of gas known as high-velocity clouds. These are not the slow, predictable structures we might expect. They are massive, fast-moving collections of primarily hydrogen gas, hurtling through space at speeds that can reach hundreds of kilometers per second, often on trajectories that seem completely unrelated to the rotation of any known galaxy. Their very name comes from the fact that when astronomers first detected their radio signals, the velocity of the gas was so radically different from the expected motion of the Milky Way's own material that it was initially assumed the instrumentation was faulty. We now understand these clouds as a distinct and mysterious population of celestial objects, and their origins present a compelling puzzle, with some appearing to be fresh material falling into our supercluster for the first time, while others seem to have been violently ejected from their home galaxies by a force we have yet to identify. To grasp why these clouds are so baffling, we need to understand the standard model of a galaxy's life cycle. Galaxies are often pictured as isolated islands, but they are more accurately seen as dynamic engines that constantly consume fresh gas to fuel new star formation, and in violent events like supernova, eject processed material back out into space. This cycle of inflow and outflow is a fundamental part of galactic evolution. However, the high-velocity clouds we observe don't fit neatly into either category. Their sheer mass, their incredible speeds, and their locations far from any obvious source defy simple explanations. They are the celestial equivalent of finding a fully stocked, speeding freight train barreling across an open prairie with no tracks leading to or from it, leaving us to wonder where it came from and what powerful engine set it in motion. One faction of these clouds appears to be intergalactic immigrants, fresh matter falling into the Virgo Supercluster for the very first time. These are believed to be reservoirs of primordial gas, cold and relatively uncontaminated by the heavy elements forged in stars. Their composition is a critical clue. They are metal-poor, meaning they contain far less oxygen, carbon, and iron than the gas found within an evolved galaxy like our own. This suggests they have been drifting in the lonely voids between superclusters for billions of years, never having been processed through the stellar forges of a galaxy. Their infill is a vital part of cosmic ecology, providing the raw fuel that will one day birth new generations of stars. The mystery lies in their journey. How do these vast clouds of gas remain coherent over such immense timescales and distances? The prevailing theory is that they, too, are held together by their own dark matter halos, miniature versions of the scaffolding that holds galaxies together. This invisible gravitational anchor would prevent the cloud from simply dissipating into the void, shepherding it on a billions of years-long journey until it finally crashes into a galaxy like our own, delivering a payload of pristine star-making material. Yet, other high-velocity clouds tell a completely different and more violent story. These clouds are metal-rich, brimming with the heavy elements that can only be created in the hearts of stars and scattered by their explosive deaths. This composition is a clear fingerprint, marking them as material that was once intimately part of a galaxy. These clouds aren't falling in, they are screaming out, having been ejected from their home galaxies with tremendous and unexplained force. The question is, what cosmic cannon could launch such a massive payload? Supernova explosions are powerful, but they tend to create hot, expanding bubbles of gas, not the coherent, often cool and massive clouds we observe. The leading suspect is a process involving the supermassive black holes that reside at the centers of most galaxies. When these monsters are actively feeding, they can power immense jets and outflows that blast material clear out of the galactic gravitational well. Another possibility is the cumulative effect of thousands of supernova occurring in a starburst region, creating a powerful galactic wind that can push gas out into intergalactic space. The true enigma is that some of these ejected clouds, like the famous Smith cloud located in our own vicinity, are on trajectories that suggest they will eventually fall back into their galaxy of origin, like a gigantic boomerang made of gas. This creates a fascinating picture of a galactic fountain where material is ejected out of the galaxy's disk, circulates through the halo, and then rains back down in a different location. This process could effectively redistribute material, enriching the outer layers of a galaxy with metals and potentially even seeding star formation in new areas. The high-velocity clouds are therefore more than just bizarre, fast-moving anomalies. They are critical components of a galaxy's circulatory system, governing its growth, its chemical evolution, and its ultimate fate. They are the stark embodiment of a universe in constant, dynamic flux, where even the vast spaces between galaxies are alive with movement, and where the line between construction and destruction is constantly being rewritten. But if the satellite plane problem challenges our models on a structural level, This next enigma strikes at the very heart of the connection between dark matter and the galaxies it is supposed to birth. Our most sophisticated supercomputer simulations of a dark matter universe don't just predict a swarm of small subhalos. They also generate a population of the largest, most massive dark matter subhalos. These are the true behemoths of the simulated cosmos, the too-big-to-fail structures. The name itself is a declaration of their expected destiny. With that much immense gravitational pull from their incredibly dense dark matter cores, these subhalos should be the absolute prime real estate for galaxy formation. They possess more than enough gravity to easily pull in vast amounts of gas, compress it, and ignite furious waves of star creation. According to every rule of astrophysics we have, these subhalos should host the brightest, most massive, and most spectacular dwarf satellite galaxies in the entire halo of a giant like the Milky Way or Andromeda. Yet, when we look out into the real night sky within our local supercluster, we find a reality that is starkly and perplexingly empty. The most massive dark matter subhalos predicted by the simulations appear to be completely devoid of their luminous counterparts. It's as if our cosmic blueprint called for the construction of gleaming skyscrapers at specific prime addresses, but when we arrive at those locations, we find nothing but empty lots. The dark matter halos are there. We can infer their presence and mass through their gravitational effects, but they are dark, failing to light up with the brilliant stars they should, by all rights, contain. This too-big-to-fail problem is a direct confrontation between the stunning success of the dark matter model on the largest scales and its potential failure on the scale of individual galaxies. So what is preventing these gravitational powerhouses from forming stars? Scientists have been exploring several compelling and increasingly nuanced solutions. The leading theory involves the complex and often destructive influence of a galaxy's early environment. While a subhalo may have the gravitational muscle to attract gas, that gas can be sterilized before it ever gets a chance to collapse. In the early, violent universe, the space between budding galaxies was flooded with intense ultraviolet radiation from the first generations of incredibly massive hot stars. This radiation, capable of breaking apart hydrogen atoms, could have heated the gas within these subhalos, preventing it from cooling down and condensing into stars. It's like having a perfectly fertile field for planting, but a perpetual heat lamp overhead that evaporates every drop of water before a seed can sprout. Another powerful factor is the gravitational environment of the host galaxy itself. As a massive subhalo orbits within the larger dark matter halo of a galaxy like the Milky Way, it experiences intense tidal forces. Think of it as a constant gravitational squeezing and stretching. This tidal processing can actually strip away the dark matter from the outer layers of the subhalo, making it less massive and less effective at holding onto its gas over time. Furthermore, the mere act of falling into a larger galaxy presents a brutal challenge. When a subhalo plunges into the hot, diffuse plasma that surrounds a big galaxy, the circumgalactic medium, it faces a scorching headwind. This process, known as ram pressure stripping, can efficiently blow away the gas reservoir of the incoming subhalo, leaving its dark matter core intact but utterly starved of the raw material needed to build stars. The subhalo arrives in the galactic neighborhood already bankrupt, its potential for brilliance scraped away during its journey. There's also the fascinating possibility that our understanding of dark matter itself needs a slight adjustment. The standard model assumes dark matter is cold and collisionless, meaning the particles pass through each other without interaction. But if dark matter had even a small tendency to interact with itself, it could change the internal structure of these massive subhalos. Self-interacting dark matter might lead to denser cores that are even more efficient at forming stars, which would make the problem worse, or it might cause the cores to become more diffuse, reducing their gravitational grip on gas and making it easier for that gas to be stripped away. The too big to fail problem is therefore a critical testing ground not just for astrophysics, but for the fundamental properties of the universe's most mysterious substance. It forces us to move beyond simple gravitational maps and consider the full, rich, and often hostile history of the cosmos, where a structure's potential is only one part of a much more complex and dramatic story of survival. Now we turn our focus from the grand architecture of dark matter and galactic motion to the very building blocks of the cosmos, the stars themselves. Within the bustling stellar metropolises and quiet dwarf galaxies of the Virgo Supercluster, astronomers are finding individual stars that tell stories which completely contradict the established narrative of cosmic chemical evolution. We call this the mystery of anomalous stellar populations, and it begins with a fundamental principle we thought we understood: nucleosynthesis. This is the process by which stars forge heavier elements in their cores and then scatter them across space when they die, enriching the cosmos with each generation. The first stars, known as Population 3, should have been pure hydrogen and helium. Then, their supernova death should have seeded the gas that formed Population 2 stars, which are metal-poor but contain those first heavy elements. Finally, that enriched gas should have given rise to metal-rich Population 1 stars like our Sun. It's a clean, logical cycle of birth, death, and rebirth that has been a cornerstone of astrophysics for decades. But the universe, it seems, delights in breaking its own rules. Deep within the faint, ancient dwarf galaxies that orbit the Milky Way and Andromeda, astronomers have discovered stars with chemical signatures that are utterly baffling. Some of these stars possess amounts of certain heavy elements, like strontium, barium, and europium, that are far too high for their extremely low overall metal content. It's the cosmic equivalent of finding a primitive Stone Age tool that has a perfectly manufactured microchip embedded in it. According to our models of nucleosynthesis, producing these particular elements in such abundance requires the extreme conditions of a very specific type of supernova or the merger of neutron stars, events that should not have been common in the earliest, most pristine epochs of the universe. These stars appear to have formed from gas that was contaminated by a highly specialized, incredibly powerful, and yet unknown polluter, one that operated before the standard chemical enrichment cycle had even properly begun. Another profound anomaly comes from stars that simply appear too old for their galactic neighborhood. Our cosmological models provide a clear timeline for the formation of large structures. The largest galaxies, like the giant ellipticals at the heart of the Virgo cluster, are thought to have built up over time through a hierarchy of mergers between smaller galaxies. Therefore, the stars within these giant galaxies should show a range of ages, reflecting this long and violent assembly history. However, detailed observations of the starlight in galaxies like Messier 87 reveal a surprising and unexpected homogeneity. A significant fraction of the stars in its outer halo appear to be almost uniformly ancient, all formed within a very narrow, early window of time. This is not what the hierarchical model predicts. It suggests that these colossal galaxies may have formed their stellar halos in a single, rapid, and immensely efficient burst of star formation at the very dawn of the universe, a process far more abrupt and monolithic than our simulations can easily produce. Perhaps the most startling chemical fingerprint of all is the mysterious variation in the ratios of certain elements that we thought were always produced together. For example, alpha elements like oxygen, magnesium, and silicon are forged in the violent deaths of massive stars in core collapse supernova. In contrast, iron peak elements are produced in larger quantities by the thermonuclear explosions of white dwarf stars, known as type Ia supernova, which take longer to evolve. Because of this delay, the ratio of alpha elements to iron in a star acts as a cosmic clock, telling us how quickly the gas it formed from was enriched. In many stars within Virgo's galaxies, this ratio is completely out of sync with the star's other properties, like its age or overall metal content. Some stars show the chemical signature of a very rapid enrichment dominated by massive stars, yet they exist in environments that should have had a much more prolonged and mixed history. It's as if the recipe for these stars was written by a chef who only used half the ingredients, completely ignoring the standard instructions for how a galaxy is supposed to cook. So what processes could possibly account for these chemical outliers? One compelling idea involves the concept of biased star formation. In the chaotic early universe, it's possible that the first supernova did not evenly enrich the surrounding gas. Instead, they might have created vast bubbles of highly enriched material right next to pockets of completely pristine gas. Stars forming on the border of these two regions could then inherit a bizarre and specific chemical makeup, a strange cocktail of the old and the new. Another fascinating possibility points the finger at the first generations of stars themselves. What if the very first stars, the population 3 giants, weren't all identical? Some may have rotated at incredible speeds, or possessed massive magnetic fields, or exploded in entirely new classes of supernova that produced a different yield of elements than our current models allow for. The anomalous stars we see today could be the direct descendants of these exotic, long-dead progenitors, carrying a chemical memory of a type of star we have never directly observed. There is also the dramatic possibility of external enrichment from a wandering neighbor. A small dwarf galaxy might have had the incredible luck or misfortune of drifting too close to a nearby hypernova or a gamma ray burst from a massive star in another galaxy. Such an event could have showered it with a specific wave of newly forged elements, imprinting a unique chemical signature on its gas just before it formed its next generation of stars. This would make these anomalous stars not native to their galaxy, but rather the children of a catastrophic intergalactic event, their very atoms bearing the scar of a violent encounter that occurred light years away. Each of these stars is therefore more than just a point of light. It is a fossilized record of the most extreme and poorly understood events in the early universe. They are challenging us to rewrite the story of cosmic chemical evolution, revealing a past that was far more complex, varied, and violently creative than we ever dreamed. But if the crowded, violent core of the Virgo cluster represents one extreme of galactic existence, then the cosmic voids represent the polar opposite, immense, achingly empty regions that make up the vast majority of the volume in our supercluster. These are not simply gaps, they are staggering deserts of space, colossal bubbles in the cosmic web that can stretch for hundreds of millions of light years and contain almost nothing. Conventional wisdom tells us that galaxies living in these profound emptinesses should be the ultimate cosmic hermits, undisturbed, unevolved, and pristine. Shielded from the gravitational harassment and gas-stripping violence of the cluster environment, they should be like time capsules, preserving the simple, quiescent state of the early universe. Their isolation should mean a quiet life, free from the dramatic interactions that trigger star formation and reshape galaxies elsewhere. Yet, when astronomers finally managed to locate and study these incredibly rare void galaxies, they found a reality that was utterly confounding. Instead of a population of quiet, faded relics, many of these isolated galaxies are bursting with vibrant, vigorous life. They are forming new stars at a rate that rivals or even exceeds their cousins in the dense urban centers of clusters, their spiral arms awash with the brilliant blue light of massive young stars. This is the deepest paradox of the void phenomenon. In the emptiest places in the universe where raw materials are scarcest, star formation is happening with unexpected efficiency. It's the equivalent of finding a lush, thriving oasis in the middle of the Sahara that is somehow more productive than a well-watered river delta. This observation strikes at the core of our understanding of how environment dictates a galaxy's evolution, forcing us to ask what fundamental processes we have been overlooking. To solve this puzzle, we must first consider the unique fuel situation for a void dweller. In the dense environments of clusters, the process of ram pressure stripping acts like a constant, scorching wind, efficiently blowing away a galaxy's cool gas reservoir, the very fuel for new stars. A void galaxy experiences no such hostile pressure. Its immense isolation means it can hold onto its primordial gas for billions of years, building up a deep and extensive reservoir. But having a large tank of fuel is one thing, having an efficient engine to convert it is another. The trigger for star formation is often a gravitational nudge, a close encounter with another galaxy that compresses gas clouds and initiates their collapse. In the void, such interactions are incredibly rare. So what is kick-starting this prolific star formation? The answer may lie internally. Without external disturbances, the dominant force shaping a void galaxy is its own gravity. The slow, steady process of its own rotation and the gravitational instability within its massive gas disk may be enough to spontaneously ignite star formation in vast waves, a self-sustaining cycle of creation that requires no outside intervention. Furthermore, the very nature of the void itself might be providing a hidden advantage. The prevailing theory of structure formation suggests that the first galaxies were born in the densest knots of the cosmic web, while the voids were truly empty. However, the few galaxies that did manage to form in these underdense regions may have done so within unusually massive and dense dark matter halos, the gravitational anchors that were just strong enough to pull in the sparse gas of the void. These king-of-the-hill galaxies would have had a monopoly on all the available material in their vast territory, allowing them to grow to a significant size without any competition. They evolved in a quiet nursery, free from the bullies that would have torn them apart or stolen their gas in a more crowded neighborhood. This combination of a massive dark matter halo and a huge, untouched gas reservoir creates the perfect conditions for a galaxy to become a prolific yet isolated star-forming powerhouse. The void phenomenon teaches us that isolation is not a death sentence for a galaxy. It can be a gift, providing the stability and resources for a long, productive, and surprisingly vibrant life, completely rewriting the rules of how we believe galaxies live and die. And perhaps the most fundamental cosmological assumption of all is now being tested by the very motions and structures we see in our local universe. For centuries, science has been guided by the cosmological principle, a foundational pillar that states the universe on its largest scales is both homogeneous and isotropic. Homogeneous means the matter is evenly distributed. No matter where you go, the universe looks the same. Isotropic means it looks the same in every direction. There are no preferred viewpoints or special axes. This principle is not just a philosophical ideal. It's the essential bedrock upon which our entire model of the Big Bang and cosmic expansion is built. It allows us to extrapolate from what we see in our limited corner of the cosmos to the universe as a whole, assuming that our location is utterly typical and unremarkable. It is the reason we can talk about the universe having a single density, a specific age, and a uniform expansion rate. Without this principle, cosmology as a science becomes incredibly difficult, if not impossible. Yet, a growing body of evidence, much of it drawn from precise observations within the Virgo Supercluster and our local cosmic neighborhood, is beginning to question this very foundation. The first major challenge comes from the sheer scale of the structures we are finding. The cosmic web is not a uniform foam. It is a hierarchy of clusters, filaments, and voids. But just how large can these structures become before they violate the idea of homogeneity? The discovery of the Laniakea Supercluster, which encompasses Virgo and stretches over 500 million light-years, was already pushing the limits. Then came the South Pole Wall, a gigantic filament of galaxies nearly 1.4 billion light-years long. And even more colossal is the Hercules Corona Borealis Great Wall, a structure potentially spanning an almost unimaginable 10 billion light-years. These are not minor wrinkles in the fabric of space. They are continent-sized mountain ranges in a universe we assumed was a flat, sandy beach. If the universe is supposed to become smooth at the largest scales, why do we keep finding structures that are a significant fraction of the observable universe itself? The very existence of these gargantuan formations suggests that the transition to homogeneity might occur at a much larger scale than we thought, or perhaps not at all. The second, and potentially more damaging, line of evidence comes from the peculiar motions of galaxies, the same ones we discussed that are pulling us toward the Great Attractor and beyond. Remember, the Hubble flow describes the clean, uniform expansion of the universe. Peculiar velocities are the deviations from this flow caused by the gravitational tug of nearby matter. In a perfectly homogeneous and isotropic universe, these peculiar motions should be small, random, and cancel each other out when we look at large enough volumes. However, when we map these flows on the scale of hundreds of millions of light years, we do not find randomness, we find coherence. We find bulk flows where vast swaths of space, containing thousands of galaxies, are all moving together in the same direction, as if caught in a single, immense current. The pull we feel toward the Shapley supercluster is part of one such massive flow. The existence of these coordinated motions on such gigantic scales implies that the gravitational landscape of the universe is not even. It suggests there are density gradients, imbalances in the distribution of matter, that are orders of magnitude larger and more influential than the cosmological principle should allow. The universe on these scales appears to have a gravitational grain, a preferred direction dictated by these immense, unseen concentrations of mass. This leads to the most direct statistical test of the principle counting galaxies. If the universe is homogeneous, then the number of galaxies in any given large volume of space should be roughly the same. Several ambitious sky surveys have now done this count, and some have returned a startling result. They suggest a dipole asymmetry in the distribution of galaxies, a noticeable hemisphere in the sky that seems to contain more galaxies than the opposite hemisphere. This would be a clear violation of isotropy. It would mean the universe has a lopsidedness to it, a preferred direction with more stuff. While the evidence for this is still debated and could be influenced by observational biases, its mere possibility is deeply troubling for the standard model. Furthermore, some studies of the cosmic microwave background, our snapshot of the infant universe, have also hinted at a preferred axis, often nicknamed the axis of evil, around which some of the largest fluctuations seem to align. If these anomalies are real and not just statistical flukes or remnants of foreground contamination, they would imply that the seeds of cosmic inhomogeneity were planted at the very beginning, challenging the isotropic initial conditions of the Big Bang itself. So, what are the implications if the cosmological principle is indeed flawed or only an approximation? The consequences would be nothing short of revolutionary. Our entire calculation of the basic parameters of the universe, its age, its expansion rate, its composition rests on the assumption that we can apply our local measurements uniformly everywhere. If the universe is not the same in all directions, then the Hubble constant we measure here might not be the same as the value in a different supercluster. The amount of dark energy we infer could be overestimated or underestimated because we're misreading the large-scale curvature of space. We might be like deep sea fish trying to understand the ocean by assuming our small, dark corner is representative of the whole, unaware of continents, atmospheres, and sunlight above the surface. It would force a complete overhaul of our cosmological models, requiring us to define our position within a larger, anisotropic structure and fundamentally rethinking how we do cosmology. The Virgo Supercluster, therefore, is more than just our home. It is our primary laboratory for testing the most fundamental assumptions about the nature of the entire cosmos. The structures and motions within it are not just local curiosities. They are the clues that could either solidify our foundation or reveal that we are standing on far more complex and mysterious ground than we ever imagined. From the inexplicable gravitational grip of dark matter to the coordinated spin of galaxies within the cosmic web, from the violent rebellion of star-forming galaxies in hostile environments to the silent, ghostly presence of dark satellites that should be shining bright, these 25 profound mysteries within the Virgo Supercluster are far more than simple curiosities. They represent the very frontiers of our cosmological understanding, each one a glaring anomaly that challenges the foundational pillars of modern physics. Every unexplained radio signal, every strangely spinning galaxy, every missing baryon is a direct message from the universe, a pointed question waiting for an answer. These aren't minor gaps in our knowledge, they are chasms indicating that our current models, as successful as they are merely approximations of a deeper, more complex, and far more fascinating reality. Solving any one of these puzzles could trigger a scientific revolution. Imagine confirming that dark matter particles can interact with themselves through a dark force. This wouldn't just solve the too big to fail problem. It would open an entire new branch of physics, a dark sector with its own rules and particles. Picture finally understanding the engine behind fast radio bursts. We might discover a new type of stellar cataclysm or a previously unknown interaction between matter and extreme magnetic fields. Even resolving the Hubble tension could force us to reinvent our concept of dark energy, revealing it to be a dynamic force that evolves over time, which would completely alter our predictions for the ultimate fate of the cosmos. Each mystery is a thread, and pulling on it could unravel our current tapestry of understanding, only to allow us to weave a new one that is infinitely richer and more accurate. This journey through the Virgo Supercluster ultimately reminds us that we are living in a golden age of discovery. Our tools are more powerful than ever, yet they are revealing a universe that is stranger, more dynamic, and more humbling than we could have ever imagined. The cosmos is not a static relic to be catalogued. It is a living, breathing puzzle, and we are only just beginning to grasp its complexity. So we want to know which of these 25 phenomena captured your imagination the most. Was it the haunting Great Attractor pulling us toward the unknown, or the cosmic ghosts of ultra-diffuse galaxies that defy all categorization? Share your thoughts in the comments below, and let's keep the conversation going. Thank you for joining this exploration of the universe's deepest secrets. Stay curious, keep looking up, and never stop wondering about the endless marvels hidden in the darkness.